Hey, awesome. Before we get started, I just wanted to say a huge thank you to Gray Area, to Thorsten, and to everyone involved here to make this happen. We're super, super excited to be here, so do a huge round of applause for everyone here. Thank you. My name's Torin. I'm a creative technologist and real-time graphics artist. I actually work right now with a place called Studio Elsewhere, doing immersive installations in hospitals. I also work as an educator. For the past couple of years, I've been working at Parsons, teaching creative coding, and also classes on Touch Designer. I'm currently doing like an immersive, interactive class with them right now. And this is Pete.
Yep. Hi, I'm Peter Whidden. I'm a software engineer, currently working in the New York Times R&D lab. I do a lot of work on graphics and machine learning and kind of physics simulation projects, and excited to show you guys ShaderPark.
Yeah, so Pete and I actually met at University of Washington. And when we arrived there, we were both really interested in creative coding, but there wasn't really a community for that. I feel like there's a lot of people doing software engineering, but not a lot of like art and code. And so we actually ended up making our own group. It was called Computer Graphics and Pretty Pictures. We took ourselves very serious. And we wanted to teach creative coding to a diverse number of students. And we basically ended up teaching like P5, processing, shaders, 3JS, like a number of different creative coding platforms just to try and share those tools and make it more approachable and accessible. And actually, ShaderPark ended up being an early prototype that came out of this group. So we're really excited. Today, this is the first time this link has actually been live. So it's launching today. And we're going to give you a little intro to it. So this is the live ShaderPark website. And it's a JavaScript library for creating interactive procedural 2D and 3D shaders. And so what do I mean by that? Well, basically this piece in the background here, this piece in the background is a shader that we've made with our library. This one right here as well. We've built in some different like authoring features and also integrations with other platforms as well, like Touch Designer, 3JS, some different pieces on Glitch, and also if you want to make a NFT. You don't have to, it's okay. And we've created a number of like interactive pieces of documentation and a whole live coding interface that we're going to get into shortly. But before we do that, we actually wanted to go into some of like the backstory and some of the inspiration and how we got into that, and then we'll do some live coding for y'all. So inspirations. We were very inspired growing up from tools and communities like P5 and processing. I feel like they made these types of environments accessible to artists and put things into terms that artists could use. P5 brought it to the web, and then tools like 3JS allowed us to be able to have 3D and in a very shareable way. That was huge. And ShaderToy was also super, super important in this space.
Yeah, so I think ShaderToy is definitely like probably one of the biggest influences for this project. Just sort of like the amount of like procedural content and like creative like 3D work that is constantly happening on that site, as well as like the community of people that are like sharing and like building off of each other's stuff is just like super cool. And that was like, yeah, sort of the main driver that we wanted to create something similar to that.
Yeah, and modeling off of the different communities as well that we saw from these different creative coding platforms. So yeah, I guess the next thing we wanted to cover is also like some of the technique behind how we're creating the graphics in ShaderPark. So Pete's going to talk a bit about that.
Yeah, so a lot of the 3D content that you see on like ShaderToy is created with this method called sign distance fields and ray marching, and essentially it's a representation for, it could be 2D or 3D geometry that is implicit, which means that rather than sort of traditional 3D graphics where you have a mesh that's a bunch of triangles and vertices that's like sort of fixed level of detail. A implicit geometry is defined by an equation sort of indirectly, and it allows you to basically generate as much detail as you want at render time. And there's a lot of other really cool properties of SDFs in how you can sort of distort them, combine them, compose them, and they have like a lot of great properties that let you do a bunch of cool modeling and effects with them. And so the project started off initially was we saw the content on ShaderToy, and
this is for, I guess, some background on like ray marching specifically. Yeah. If you want to talk a little bit about that.
So this is sort of a visualization. This is actually a ShaderToy made by a ShaderToy user, which shows sort of the process of how ray tracing works in the context of ray marching. You may or may not be familiar with this stuff, but the SDF representation allows you to use this algorithm called ray marching to do ray tracing where you cast a ray through your scene, and you do this for all of your pixels on the screen, and that's how you can render an image using these implicit representations.
Yeah, that was who made that.
So the way that you do modeling with SDFs is with sign distance fields is that you essentially have equations that define different geometries, different primitives, and this generally can be kind of like math intensive. And the creator of ShaderToy, actually, Inigo Quilez, has a bunch of examples, and he has like articles on his website that show like a bunch of derivations of all these different primitive geometries, but ultimately, like, you sort of end up copying and pasting or like rederiving a lot of this stuff over and over, and that's kind of like how things happen on ShaderToy. This is actually an example of a piece by Inigo Quilez that he actually started in part of a workshop that we organized with him when we were doing our graphics group at UW, and this is a really impressive example of what is possible if you're like
one day.
Yeah, like he's an amazing artist where this image essentially is created entirely with code. There's no textures or 3D models used to create the image. It's just a big equation, a block of code essentially, where it's like you have your X and Y coordinate, and using those numbers, you just calculate what the color is going to be, and it's pretty amazing what's possible if you start to like become comfortable with the medium. So it has a lot of potential and interesting things that you can make with it. And this sort of brings us to the origin of Shader Park was that on ShaderToy, there's, like I mentioned a moment ago, lots of cool examples, but you're sort of bringing in all this boilerplate every time that you want to create something, and there's a lot of overhead to creating stuff. So we just thought it would be fun to have a setup where you could do not just like a single ray-marched object that's like sort of your standalone thing, but actually put it into a larger 3D environment and have like multiple of these objects in one place, because generally you don't like, it's not like you get a mesh that you can just import somebody's mesh. You have like a bunch of shaders, and it's not so straightforward how you take that and put it into a common environment. So that sort of led to these early prototypes.
Which we could only find the scrappiest videos of.
Yes, unfortunately. It may be revived someday, but the remaining media is not super high quality. Anyway, so this is an example showing of this sort of like virtual environment, which is actually this like multiplayer, like persistent world of like this like sort of virtual art gallery where you'd fly around and have like all of these shaders running live, and you could basically just walk up to them and click on them and like edit the code. And as you edit it, like your code would get pushed out and compiled immediately to the other people, so you'd like see people writing on the things. Unfortunately, that's like a very difficult approach to sort of scale up into like more features.
So we ended up doing like a full redesign of this, and then pushed it into a larger context. But I guess touching on
so first
this
though,
piece,
this is sort of noting what I was mentioning before about like sort of boilerplate and a lot of setup. This is an example of a ray-marched geometry that I made yesterday actually, and this is sort of demonstrating if you were to, this code isn't all supposed to be readable, but this is demonstrating if you were to do this from scratch using just GLSL, the sort of native shader language, from scratch like on ShaderToy, this is all the code that would be involved. And it's, I don't know, a pretty substantial amount, and a lot of it is very math heavy. And the key thing too is that a lot of this would be basically the same if you were creating different things. There's kind of just like boilerplate to set up this environment to render these things.
So we worked a lot on creating this core library early on, and this was initially in GLSL to simplify that process. So you wouldn't have to write nearly as much. Like a lot of the helper functions were built in for you that you could then use.
So in addition to putting all of this stuff into the main space, the sort of next thing was that, okay, like everything on the site is going to be ray-marched and 3D, so we can just factor out all of that boilerplate code, and then it becomes much more manageable. You can just like prototype, start things up quicker without having to get it all working from the beginning.
Then we did a redesign and tested it out with more complex shaders, and this was our initial test. But then promptly, we realized that it was really difficult to navigate the little virtual environment. So we ended up switching it to more of a 2D interface for our setup. And that kind of brought us back to revisiting like the core functionality of the library and just figuring out like how we can make it more approachable to people.
Yeah. So we were doing sort of a redesign of like the usability of the site anyway. And when we were doing this process, we were realizing still like, okay, like there was still an inherent amount of sort of overhead to working with this medium of creating SDFs that just like didn't feel as efficient as it could be when you're writing just raw GLSL code. And that's when we basically got the idea to say like, is it possible to use another language to actually generate the GLSL that allows you to more concisely describe the same SDFs and not actually like compromise like what you can do, sort of the expressiveness. And that's when we sort of were able to, we made the first prototype of the library that would actually let you write the shader in JavaScript and not kind of just like sort of tweaking some of like the high level stuff, but actually like writing your mathematical expressions in it, writing stuff like a loop and like using functions and like some of the higher level features of JavaScript and actually being able to generate your GLSL code using much less. And this was sort of inspired as well by processing and its sort of imperative API where you can just create primitives and there's sort of this stateful rendering where you're like changing your coloring, your material, displacing, moving your transform and stuff. And we actually will show a bit of that now, what it looks like to like work with this medium in sort of a live coding setup. Yeah, let's see.
It's not good.
Put this up on the thing maybe. Cool, yeah. I'll also just show here as well what the interactive documentation looks like. So we have basically this is like documenting how some of the library works, and all of these have basically interactive demos that show how each of these works, so you can see basically like working examples which show how to use different parts of the API, and you can just basically live edit these things. So if you change these parameters, you can just like take the examples and start modifying them. As you can see, there's like very, very little boilerplate to actually just start creating this type of geometry. And yeah, going back over here. Yeah, so for example, we have different primitives. Do like box, you can do torus. Pan this around. And one of the fun things too is that because these are real-time shaders which are like compiled on the fly and like running every frame, you're not actually just creating a static like object, a mesh, but it's actually all of these are like automatically can be animated as simply as they are created essentially. Like animation and interactivity is just sort of like built in by default. And just demonstrating a little bit more of how this works, you can use a function like displace to do just like basic translation, for example.
I'm going to bump up the text size.
Oh yeah, that will help. Thank you. So you can see here I'm just moving this around. Again, just as easily as I do this, we can also make animation, so it's moving up and down. And one thing that's like, okay, so this is, probably looks just like basic kind of 3D stuff like you could do in any 3D engine. And a really interesting addition here is we can basically get our coordinate system here. So this is going to capture our coordinates, and this displace function, when you just put in constant numbers, will give you essentially a translation, but you can actually parameterize how you're translating based on space. So for example, I can adjust the X translation based on, say, an oscillation in our Y coordinate. Let's see. Actually going to do Z. So now we've deformed our torus here. And then we can also obviously just animate that as well. And another fun thing, so it's really easy. I think one of the things that's like really nice compared to working with SDFs in raw JLSL is you can just sort of create them. You don't have to think about like keeping track of your distance calculation as you're moving along. And we can actually do, one of the really cool things that we can do that I think is unique to SDFs is constructive solid geometry, which is basically the ability to sort of take solid objects and do addition, subtraction, intersection between these solid objects. So for example, I will just disable this for a moment. I'm actually going to swap the order of these. But I can do, for example, I can set our geometry mode here to difference. And I'm actually subtracting the torus off of this sphere here. And if I bring this back in here, let's see, actually, let's just do something like this. Yeah, so it's like dynamically, if you were doing it with a mesh, you'd have to be like regenerating it all the time and be like very complicated, but it's like very sort of simple and elegant using this setup. You also have other things to sort of just like basic manipulations, translations of your geometry. Rotate Y is not going to do anything because it's symmetric. So this is another thing that's really interesting that we can do this. And we also, another cool sort of integration of this system is we have an actual materials, like PBR-based materials in this as well. So that's also something that if you wanted to set up yourself, might take some time if you're trying to do this in like a Raymart shader. But that's just sort of enabled and built in by default, so I can change material properties. We can do the albedo of this like this, and we can also, of course, parameterize this on our space, of course. It probably would look a little better if I do this. Actually, I'm just going to leave that for now. And there's also a lot of really interesting algorithms built in besides just these sort of like geometry-related things. So, for example, we have noise functions. And for example, I can just get simplex noise based on our like coordinate, for example, just like this. And if I want to say, visualize that with color, I can do this. Let's scale this up a bit. And now we have simplex noise on our object, and just as easily we can also actually, let's do this here. So this is what's fun, is that you're essentially writing a shader here, and you have like the material and the geometry and any other calculations sort of all sharing the same scope, essentially. So I can like create some variable noise, I can apply it to the material properties, and I can also apply it to the actual geometry itself here too. And of course, this is also animatable, just like everything else is too. So it's really fun to be able to just like take these variables and have them all into the same scope here. There's.
Can I show shape?
Yeah. Do you want to?
Yeah, let's do it.
Okay.
One other piece that's really fun here as well is like we have like this object. We're able to use constructive solid geometry here to like make the sphere and then cut the torus out of it. And you're kind of entering into these different modes, right? So like I'll take the difference, but then what if I want to use that constructive solid geometry with another shape? And one thing that we were really interested in is kind of like building off of the structure of JavaScript. So imagine you can take all of this and kind of encapsulate everything together. We really wanted to make these kind of reusable chunks. And so what we ended up doing is setting it up so that you can just use functions like you normally would in JavaScript, and you just wrap it in a little helper. So yeah. I can
describe a little bit.
Yeah.
We implemented this form of encapsulation, basically, where what we initially were doing when you're using this setup where you have this sort of stateful updating your drawing mode, like you're setting your color, you're setting your like coordinate system, you're distorting it, and that is great, but then if you want to draw some other separate object, then you sort of have your state all like manipulated, and it's nice to be able to sort of like do a bunch of state manipulation on some object, but then create something else. Yeah. So we basically have this method to take any set of commands and essentially capture all of the state that's happening in those commands and basically wrap it into a new primitive. So the same way that you can create a sphere or a torus, if you encapsulate any sequence of commands into this shape function, you've basically created a new primitive which you can now use and has the same properties as your base primitive. So this allows you to do things like hierarchical modeling, where you can have objects nested inside of each other. and to use your like composite models or shapes in other CSG operations, and just like moving back and forth between other people's projects. It's like if you want to bring someone's SDF in, it might not be so straightforward if they have their own custom bespoke ray marcher, but when you have like this encapsulated shape, it's like very portable between any other piece that you're trying to move it from.
The other thing we can do as well is like we can use this, and now we can we continue to build other shapes and then use those constructive modes. So I could, for example, like make a box. And it's a little bit smaller, so we can't see it right away. There we go. But now, like, imagine, right, this is one of my favorite operations to use, is you can actually blend between two different shapes. Mm-hmm. So I can do mix geo, and now if I pass it an amount, it goes, right now it's like halfway between those two shapes. So if I go 0, it's the box. If I go to 1, now it is the sphere. And then we can use this. I think what I'll do actually is also pass these into our shape here. I think that will help us out. But you can also parameterize this. So now we can kind of like blend between those different objects. Yeah, and the same thing goes with like the material properties too. So like you could set up the shading for one object, another object, and then also blend between those materials.
I think, yeah, just for reference to it, it's nice to show just like the blending between, just say, a sphere and a cube, I think is a good demo. And yeah, this is like one of the cool properties of SDFs is that you have this ability to do this very kind of like seamless transition between two geometries. And obviously this works with primitives, but it also works with any more complex thing that you create too. So if you have some crazy geometry you've created and some other crazy one, you can actually just interpolate their geometries in a very smooth, continuous way, which is a fun property of SDFs. And we're not going to go into like a full like workshop level like exploration of all the different features, because there's a bunch of different cool operations which we aren't going to have time to cover and show, but we can also just put up a couple other examples, I think, here of interesting things. So this is using mirroring as well as some other features where you can essentially reflect, have like symmetry essentially, where you can create across a plane, mirror everything. So this is, yeah, it's based on like, really it's only rendering a single cube, but you can take your coordinate space and essentially create symmetry. So we just have like a for loop here, right? If you change the like iterations, if you do like,
just a couple.
Yeah, so it's parameterized, and that's always like, as I'm sure many of you know, the fun of procedural art is that you can parameterize all of your creation and then like create your own controls and just like regenerate the whole thing, which is really fun. Here's another example too of sort of like, this is just sort of showing that like here's a single, it's really like, if you look at the code, it's rendering a single sphere. There's a bit of math that was brought in externally on this one, but just sort of demonstrating. If you actually look at the code, there's only a single geometry call, but there's some calculations being done to sort of like do like a random color and transformation at different points in space, and then like replicating your coordinate system. That actually looks a bit nicer. I think you improved it.
We're doing great.
Yeah, this is just sort of a demonstrative one of some of the properties of SDFs where you can just take a single geometry. You can think of it maybe kind of like instancing in like a traditional rendering pipeline. But yeah, that's a cool one. Here's another example of, this is actually just a 2D shader. So even though it's like the shader park library is very oriented to be 3D, you can just as easily make 2D stuff. It works just great. So this is an implementation of a true shape pattern that also uses sort of spatial repetition, and is obviously hackable in all sorts of ways. And this might not be the most opportune moment to mention this part too, but just describing how a bit of this works, how it's possible to have this JavaScript stuff. The way that we generate the shaders, like obviously this is a live coding environment, so as you type, it's actually executing JavaScript, generating GLSL, compiling GLSL, start running GLSL, and it's just sort of the miracle of like modern like computers, browser platforms that you can do it this quickly. So we actually have this whole operation that allows, this whole like pipeline that allows us to do stuff in JavaScript that you normally can't do, like operator overloading, where you have like, say, a vector type and you want to like add or multiply it to another vector type. JavaScript doesn't allow that, so we actually have a whole thing that parses your source code, like regenerates all of the mathematical operations to special function calls, then executes that, and it's just like, I don't know, when we first set it up, I was amazed that it's possible to run this all like in real time as you type, but in the end, I was pretty amazed how the ergonomics ended up working out, despite the complexity that happens every time you're making some tiny little change.
Yeah. I think for the time that we have left, I think we just want to share a couple favorite experiments. So this one we were just working on earlier. It's a little, we basically wanted to see if you could create a volumetric renderer using JavaScript.
This is, yeah, this
worked. It was.
Oh, yeah, this is a fun example because generally you have sort of this like fixed setup for ray marching, but you can also just sort of like, you can see there's this no lighting thing, and you can basically just bail out of all of the boilerplate that we've set up and just do your own calculations and put stuff there and still use sort of the JavaScript language, like the higher level language, without using all of the ray marching stuff. So this is an example of just bailing out of the actual ray marching, writing our own volumetric renderer with, you know, still using the built-in like library of noise functions and stuff. So this is like, it's just this like, you know, 20 lines of JavaScript, and it's an actual GPU implemented volumetric renderer, and it's live codable, and I think that's really fun. Here's another example just of, this was actually pre the JS API, but this is an experiment I did making a volumetric renderer for the probability distribution function of the hydrogen atom. So this is just a screenshot. There's a demo on the site, but essentially it's a parameterized electron cloud density in the hydrogen atom. So you can basically like select there's like 3 numbers that determine like an electron orbital in a hydrogen atom, and you can just like put in the number for the parameter, and it will generate and volumetrically render in real time the electron, its probability distribution, and it looks pretty too.
Another piece we got to work on is actually early on I hosted a number of workshops on Shader Park, and as a part of that we had everyone make procedural mugs, and these were so fun. It was great just to get to see what everyone made from these, and a lot of them were animated, and it was so cool just to see like the variety that everyone generated. I think this is like a little sizzle of like a couple different sculptures that we had worked on over a period of time, but also just like showing some of the different interactions. Like you can have mouse input.
Yeah, I missed that part.
You can also define your own custom distance fields as well. So if you want to create
another
your
fun
own
thing. Yeah, we didn't get time to cover is that you can still write your own.
And also, this is. We use this.
This is a recursive shader.
Yeah.
Which you can't do in JLSL.
You definitely can't do that normally. Some more volumetric tests. Looking at like loading in a keyframing library to be able to animate things.
Another feature here that we didn't really get to demo also that is somewhat new is the ability to basically put in a snippet of GLSL and automatically generate JavaScript binding for that function, which basically opens up the whole possibility of like, oh, I have like this cool GLSL code or something I found online, and if you want to port it in to use in Shader Park, instead of having to translate it into JavaScript, you can basically just put it in as a string, and we have an actual GLSL parser in the library which will pull out the type signature of the GLSL function. Here's an example of drag and dropping a material into Unity as a shader.
We also looked at using like volumetric text and then putting that into something like the Looking Glass. And some of the visuals that you were seeing earlier
display.
were like bringing in Shader Park into something like 3JS, and then like using it in combination. So like here we're rendering a museum collection, and then seeing like where this whole like
Museum
hue
collection, the little
saturation.
tiny dots are each paintings, I believe, right?
Yes, if you see them up close, actually, a lot of them, each little dot there is a museum painting, and then the idea was to have like be able to filter through the collection like a hue saturation brightness color wheel.
Yeah, mapping hue saturation value into like XYZ kind of, and then visualizing that with like an actual 3D color wheel.
And I guess to kind of wrap up some of the new features we were working on, we also got to do an event with Live Code NYC. So we put together a like strictly live coding editor for Shader Park. But then one of the things we were really interested in doing is Pete and I both wanted to be able to live code. So we built this custom interface for Shader Park that would allow us to basically have on the left side one code editor, on the right side another code editor. And you saw how we were able to mix between geometries. We set it up kind of like a DJ turntable. So both of us could be programming, and then the little slider in the center, like we could, you could have one shader, the other shader, and then you could mix between the two shaders. And the thing that was so fun is that you could also put it like halfway between the two, and then you kind of get like we can kind of improv off each other's creations from that. And
Yeah.
it doesn't have to just be mix as well. Like you could put it into different modes of like being in the displaced mode or
Yeah,
or
this
in the,
video isn't the greatest demonstration of the feature, but the fun observation is that the sort of crossfade in a DJ setup between queuing up and playing different tracks fits great with our sort of encapsulated FCFs that allow you to seamlessly blend between the two. And we actually had like this WebSocket server with like 3 laptops where one was displaying it, and 2, we were each writing like shaders on different ones, and we could then blend back and forth seamlessly between the different bits of code that we were writing.
Yeah. Yeah, and we just wanted to give a special thanks to everyone here for their feedback and inspiration on the project. So greatly thankful. Yeah, thank you, everyone.